Excellent. Thank you, Susie and John, for the invite and for setting up this series of talks. Today, I'm going to give you an update on where we are on high field superconducting magnets at Oxford Instruments. I will start by, if I can move the screen. Okay, it's not moving the first slide. Sorry.
You might need to click in that window so PowerPoint has focus.
It's nothing working.
Or try right clicking and then clicking next.
I see. Okay, good. It's very a brief overview why we are doing high field. So I will start by sharing some of our current thinking on within nanoscience, followed by a simple introduction to the evolution of high field magnets within Oxford Instruments, not outside, but really within Oxford Instruments as product portfolio. One critical element which we handled within Oxford is the quench management of compact high field systems. And then this will lead us to the introduction of a new class of high field magnets and a summary. So a little bit about history. Oxford spun out from Oxford University in 1959 by Martin Wood and his wife. And Martin commercialized superconducting materials by building the first superconducting magnet in 1960. Within 10 years, developed the first MRI body scanner. And within another decade, became a public company on the stock exchange. In another decade, we started to go into higher market in advanced instrumentation. And 2000 start to see new advanced technologies and new applications, and now we are focusing on solutions. So as a group now, we have about 28 offices worldwide in 18 countries with over 1,600 employees. There are 3 sectors within Oxford Instrument Group now: the materials and characterization, and service and healthcare, and the research and discovery. The high field superconducting magnets and cryogenic application sit within nanoscience, which previously was superconductivity and so on. And that's part of the research and discovery sector. So nanoscience, the current focus nowadays on quantum materials and technologies, advanced device development and instrumentation for physical sciences and materials applications. The primary technologies which are relevant to high field magnets are the condensed matter, 2D materials research, including graphene, scanning probe applications, and energy and quantum dots. So in one slide, summarizing what our current product portfolio and high field magnets is fitting into that regime. We have the cryogenic tools leading into application relying mainly on cryogenic systems and optical applications and high vacuum. And then that take us from 1.5 Kelvin down 4K and up to 300, 400 Kelvin if required. Then the ultra low temperature tools, which is basically focusing on sub 1K Kelvin application down to 5 milli-K. And of course, the superconducting magnets ranging between 1 Tesla to 22 Tesla, all as a product using low temperature superconductors and the instrumentation to go with them. high field superconducting magnet fit within the superconducting magnet group. And there are two types of superconducting magnet we do. We do the product families like Teslatrons and Spectromag, which is really a repeat of systems, and hence we call them a product. And we have the custom systems for special applications, and ultra high field magnet system fit into the custom applications. So the evolution of high field magnets, it's all started by this small magnet in Martin Wood's hand, and followed by a series of research magnets between the 60s and 70s. A decade later, NMR applications start to become as a product, followed by MRI. And in the 2000, we start to see interest in high field application beyond 18 Tesla. And now we are entering a new phase, a new era where people are interested in high field magnets beyond 20, 22 Tesla, going to 30 and 40, led by Florida lab and other labs in Europe as well. So Oxford is current philosophy, starting with custom systems, special projects, and with mind to make them a family of products. That's how we see all these activities leading to a family of products. So one of the critical things to think about when you start making a product, there are various factors decide on the final outcome of the system. There are three primary drivers. The customer needs, that's where we started. We start from the customer needs, what they want, the application, the size, the money available for them, the environment, and the operating conditions. From these requirements, we start to think about the engineering and the materials capabilities, what materials. So if you talk about superconducting magnet up to 10 Tesla, 11 Tesla, you start to think about certain type of material like niobium titanium. But if you want to go to higher, you have to use another material like niobium tin. And the third one, which is critical, is what engineering capabilities and techniques you have to use to deliver the final customer objective. Customers are interested in the highest performance, the cheapest cost, and the smallest footprint. Hence, we start to think about how we address these by enhancing our capability in engineering and in selecting the materials and influence materials development to ensure that we can get into this customer needs. In the end, the final product will be a compromise design, taking into account the customer needs, the materials capability, and the engineering side. So there are three critical elements required in developing high field systems: the superconducting materials and their design. So if you are dealing with less than 23 Tesla, then you can rely on LTS material. If you have to go higher, you have to start thinking about HTS. And so far, Oxford involvement is really in the R&D stage, in the prototyping, not in the product stage. The next phase is looking how about the engineering and the coil technology required. If it's compact, will require certain engineering requirement versus coil structure and the cooling techniques. Up till 2000, most of the superconducting system we were producing were completely wet system. Since for the last 15 years, we are developing cryogen-free systems. All our up to 14 Tesla now, probably 80% of our superconducting up to 14, 16 Tesla are cryo-free now. 20-30% are cryogen relied, depends on the customer needs. And if you want to go to higher than 18 Tesla, still the preference to go to wet systems for cost purposes. And of course, you need to think about how to system integrate all these requirements, competing requirements, from the predicting performance of these systems and management of energy management and coil structure and instrumentation. If the mouse can move now. Sorry, I tried to make the mouse move in the right direction. So the first, one of the critical element to think about is which wire to select for these high field systems. And there are over 4,000 superconducting materials being researched and developed across different labs in the world, but really 6 of them are of practical use. And here I'm showing the engineering current density. If you are talking about up to 10 Tesla, this yellow one corresponds to niobium titanium. Our interest in design, this dashed box correspond to the region where we would like these coils to be developed. So up to 10 Tesla, you could see the favorite will be niobium titanium. If you want to go beyond 10 Tesla, the favorite will be niobium 10. But if you want to go beyond 20 Tesla, 22, then you have to think about high temperatures like BISCO 2212, BISCO 223, and EPCO. The other development it has been done over the years is to improve the performance of these low temperature superconductors. So what we have seen about 20 years ago, most of the systems were using bronze-based niobium tin material. Oxford Instrument sister company, which now bought by Bruker, Oxford Superconducting Technology, part of Bruker now, has developed the RRB wire. And this has enabled almost a significant improvement in the performance of wire critical current density. And that's for a standard wire. You could see the significant improvement almost about by 3-4 Tesla for the same current value. And then recently, the OST has developed even the high JC performance, which means that even higher current density for the same wire size. What that means, that's enabled really us to start think how to make these systems smaller in size, and we managed to reduce their size by almost 30-40%. However, this has come at a price of coil structure and energy management to manage these high performance material in high field environment. So all this development has over the years relied on the materials. So up till 1990, it was mainly up to 18 Tesla, relying on LTS and HTS. And in the early 90s, we start to think about how we can get more high field using pumped helium, getting another 2-3 Tesla. But since 2000, we start to think about using high performance wires to take us to 22. And currently we can go up to 20 Tesla with wide bore at 4K, and that's significant improvement. The future is now we start to see the emergence of going to higher field beyond 22 Tesla. Florida has demonstrated 32 Tesla using LTS outsert plus RIPCO insert developed by Florida, and has been demonstrated in December 2017 and currently in the process being commissioned as a user facility. This is a major step for the community and the era of going to 30 Tesla as a material for high field systems are within our sight. So one of the, I mentioned about the quench management, this is a set of voltage traces we modeled and measured for one of our high field system, and showing how important it is to predict the performance of these systems to ensure that your quench is safe and the operation of your system is reliable and robust under various operating conditions. So what I'm showing here, a titanium coil is quenching, pumping the tin coils, and the quench management activated to ensure that the voltages are within the capability of the isolation, electrical isolation of these coils. And this particular new class of high field magnets, we only have one spontaneous quench niobium titanium coil with no quench in tin coils at all. And after a thermal cycle, we haven't seen any quench. And that represents a major step in management of these superconducting magnets, especially tin coils, where you can now process them and ensure that they survive a quench with no trailing behavior. That's one of the critical elements. In the early days of high field magnets, repeated training of the 10 coils has made it quite a difficult exercise to produce reliable products. Now we do that routinely. So one important aspect to look at is how these affecting the hotspot. So in this particular scenario, when we have a quench in the outer coil, we can see the impact on every single coil within the magnet. These are ribbon showing the transients on high temperature within the magnet, which is within the design guidelines. At the same time, the transient currents within with these coils, you could see them, they are building up in the coil with quenching, and the 10 coils are not exceeding their design guideline. This is the most critical element to ensure that when you have a quench, it doesn't affect the stress and the voltages within your design criteria. So that's basically led us to have now a new class of high field systems, compact in size, and starting with 15 Tesla, 160 millimeter at 4K, led to a 19 Tesla 150. This is one of the first high field systems operating at 4K that we think with the high JC wires, we can now develop systems running at 4K with wider bores without the need to use the pumped helium and make the system more complex to run and very expensive nowadays. Secondly, we want to make sure that our designs can be adapted for cryogen-free systems as well. So these are now systems which currently in production, standard product, and they can vary from 19 Tesla 150 to 20 Tesla 100 millimeter bore at 4K. It's very slow here, the mouse. I do apologize. Okay, these are the performance of these systems. They vary in homogeneity between part NA4 to part NA5. The various applications for research magnet and for scanning microscopy. And we are starting to see the emergence of a new application like dark matter as well. So areas like research magnet are very prominent in our product portfolio, and that's really targeting the graphene research, the low dimension material research, and condensed matter research. Some of these systems has been used as outsert for higher field systems. Dresden have used it to demonstrate a 23 Tesla using a small test coil of PISCO 2212, and Florida has demonstrated 32 Tesla using the REPCO material. Recently, we just finished shipment of a 12 Tesla 320 millimeter system for dark matter to Korea. And 2 years ago, we shipped a system for STM in China, 18 Tesla 150. So there's now a family of product relying on wider bore, compact in size, and running at 4 Kelvin. The first one here, I'm showing you some of these systems. They are having energization time of 2 hours for the 19 Tesla at Dresden, less than 6 megajoule. And the helium capacity is 240 liters. That's really a significant drop in the helium needs for these systems. Now, this in itself represent another family of products. You could take the inner section and make a 16 Tesla 210 millimeter. So this gives you a versatile system where it can be used with different bore sizes. Florida have used that system for demonstrating 32 Tesla, and this is showing the robustness of these magnets. Repeated energization and quenching of an insert has been demonstrated in that system, and showed that the LTS survived repeated run of these inserts. Again, this system, 15 Tesla 250, can become a generic design for other options. We have just finished the 12 Tesla 320 based on the Florida system, which is also being commissioned for dark matter applications. This is another example of these systems. This is 18 Tesla 150 based on the 19 Tesla of Dresden, but is for scanning probe microscopy. It's a compact system with high persistence. The customer wanted high persistence. The other thing, they wanted low vibration with no nitrogen shield and low loss magnets. So they want the experiment to last 2 weeks without filling the system. So Oxford has really adapted that solution, become basically robust and provide a high performance system, high persistence and high volume performance. Here I'm showing another example of 12 Tesla 320. It has, in addition to the standard magnet system, it has a cancellation coil. Dark matter application will require a zero field region. And to do that, we have adapted the cancellation coil, and the total field cancellation extend over 100 millimeter bore, over 100 meter length, with 750 millimeter above the central field. This system has came out to be very efficient in running 300 liter of helium with 2 liters per hour, and the total weight is less than 800 kilogram. This low loss system, you could see how it is showing within 2 days the temperature doesn't exceed certain values, with helium ball off within the shield pre-cooled specification. More importantly is high persistence. It gets into the desired persistence value, the decay value, within less than 15, 16 hours. So in addition to these systems, which all are wet systems, we have a family of cryo-free systems extending to 18 Tesla at completely cryo-free with 57 millimeter bore with low vibration for graphene research at Manchester University. And in addition to that, we have provided systems which can take us to 16 Tesla in very ultra low temperature environment, and in a compact system running down to 5 milli-K. And this is we have done 2 systems with 16 Tesla with 44 millimeter bore and 57 millimeter bore in a compact system. To summarize, we have really have new technologies leading to new compact systems. It is maximizing the system value, enhancing with enhanced control, increase the experiment time and throughput, allow us to scale experiment and add other capabilities with reduced noise and vibration, and integrating magnet system for diverse applications. You could see the evolution over history from the size of this, our first 22 Tesla, done in 2005 at Oxford University for NMR, to reduced in size within 5 years. The MDAMA system, which currently used by Florida for testing HTS coils. And this is a condensed matter basic research magnet, 22 Tesla, 52 at 2K, at 20 Tesla at 4K. And this is the new class of systems which is allowing us to have integrated solenoids, vector rotate, and low temperature system, STM application, and so on into our high field program with a combat size. And thank you.